Hello everyone, welcome to this lecture series on thermodynamics. Today in our topic, we are going to discuss first law of thermodynamics, its applications and limitations. We know that first law of thermodynamics is a special form of law of conservation of energy and was first stated by Mayer and Helmholtz in 1840. According to this law, energy can neither be created nor destroyed, but it can only be transformed from one form to another process. However, in any process, the total energy of the universe remains the same. So we will see the statement of first law of thermodynamics. The first law of thermodynamics, as we have already discussed, is a special case of law of conservation of energy. That is, energy can neither be created nor destroyed. It can only be transformed from one form to another form. So one type of energy is being converted into another type of energy. It's neither created nor destroyed. So this first law of thermodynamics can be stated in two different ways. So according to first statement, when a definite amount of work is done, say W, then a certain amount of heat is produced, that is Q, and vice versa. That is, when certain amount of heat is supplied to the system, an equivalent amount of work is done. This statement establishes the relationship between heat Q and the work W. This can be mathematically written as W is equal to J into Q, where J is the mechanical equivalent of heat. This first law of thermodynamics can also be stated as in all transformations, heat energy supplied to a system is equal to the increase in internal energy of the system and the sum of the external work done. This is also known as differential form of first law. This is known as the mathematical form of first law. This is known as the differential form of first law. Here, dQ represents the amount of heat supplied to the system, du represents the change in internal energy, and dW represents the work done. So, this we have already understood that first law of thermodynamics is nothing but the special case of conservation of energy. It states that energy cannot be created or destroyed, but can be transferred from one object to another. In order to understand this, let us take some examples. When we look at some examples, we will see that the transfers and the transformation of energy takes place around us all the time. For example, we can see light bulbs transform electrical energy into light energy or radiant energy. And another example is one pool ball hits another. If one pool ball hits another pool ball, then what happens? It transfers the kinetic energy. That is, the first pool ball transfers the kinetic energy, making the second ball move. Next, coming to the next example, we always see that the plants convert the energy of sunlight. That is, they absorb the energy, that is the radiant energy from the sun, convert it into chemical energy, which gets stored in the organic molecules. So another one is, you are transforming the chemical energy from your last snack into kinetic energy as you walk, breathe, and move your finger to scroll up and down this page. So with the help of these examples, we can surely say that the first law of thermodynamics is nothing but a special form of conservation of energy. So now let's understand this with the help of the following picture. Here, the light energy is being converted into chemical energy. That is, the sunlight is being converted into the chemical energy. Here, the electrical energy is being converted into thermal energy. That means heat energy. In order to cook or make coffee, we need heat energy. Where we are getting this energy? Here, the electrical energy is being converted into thermal energy. Now look at this picture. Here, what is happening? In order to ride a bicycle, we need mechanical energy. So where we are getting this energy? We are getting this from the chemical energy. So the food we eat is being converted, that is the chemical energy is being converted into mechanical energy. A similar example of this type, in order to drive a car, we require the mechanical energy or we require the fuel. The fuel is nothing but diesel or petrol, this in the form of chemical energy. So the chemical energy is being transformed into mechanical energy. These are the best examples for conservation of energy. Energy is neither created nor destroyed, but it is being just transformed from one form to another form. So we can say that the first law of thermodynamics is a special case of law of conservation of energy. Now let's take another example where a chain of energy transfer starts within the microwave oven. Let us take a microwave oven. Let's place some food which we want to heat or cook inside the oven. Then what happens, we will see. So when we switch on the microwave oven, the electrical energy is converted into thermal energy. Then the thermal energy is nothing but the heat energy. This heat energy is being transferred to the food which we cook. That heat energy from the food is again being transferred to the environment. Now, once the food is cooked, when we eat, that chemical energy is being converted into kinetic energy. And now this kinetic energy is again used in doing the regular activities of our daily life. So what is happening? The energy transfer goes on. That is, the chain continues. So this is one of the best examples for conservation of energy. Now let's see the significance of first law of thermodynamics. According to mathematical form of first law, W is equal to JQ, we can say that heat is a form of energy in transit. That is, heat is a form of energy in motion. It gives a relationship between heat and work. Energy is conserved in a thermodynamic system, and every thermodynamic system in equilibrium state possesses internal energy, which is a state function of the system. So this is the significance of first law of thermodynamics. Now let's see the sign conventions to be followed while applying the first law of thermodynamics to various thermodynamic processes. For this, let us take up the differential form of first law of thermodynamics. That is, dq is equal to du plus dw, where q represents the heat energy, u represents the internal energy, w represents the work. dq represents the quantity of heat, du represents the change in internal energy, and dw represents the amount of work being done. Now, while applying the first law of thermodynamics, one should be careful about the signs. These sign conventions are very useful in solving the thermodynamic problems. So here, all the quantities must be expressed in same units. Quantities means Q, U, and W. All of them should be expressed in same units. Heat absorbed by the system should be taken as positive, and heat rejected by the system should be taken as negative. That means the quantity of heat entering into the system must be taken as positive. The quantity of heat coming out of the system should be taken as negative. Next, the increase in internal energy should be taken as positive. Decrease in internal energy should be taken as negative. That is, du should be taken positive if there is increase, du should be taken as negative if there is decrease. Work done by the system should be taken as positive. Work done on the system should be taken as negative. Now, coming to the applications of first law of thermodynamics to various processes. We have come across that the first law of thermodynamics is a special case of conservation of energy. According to this, the heat supplied to a system is the sum of increase in internal energy du of the system and the work done dw by the system. This can be mathematically represented as dq is equal to du plus dw. Now let's apply this to some of the thermodynamic process. The first among them is isothermal process. We know that in an isothermal process, the temperature remains constant. The temperature remains constant. When there is no change in temperature, T is constant, then change in temperature will become 0. We know that the temperature T and the internal energy U are in relation with each other. Hence, when temperature remains constant, U also remains constant. Hence, du becomes 0. Then the first law of thermodynamics in an isothermal process or for an isothermal process reduces to dq is equal to dw. dq is equal to dw. That means in an isothermal expansion process, work is done by the process. Work is done by the process. Positive work is done by the process implies that the total amount of heat is being absorbed by the system. Similarly, if work is done on the gas, then dq is the quantity of heat which is liberated in this process. So this is regarding the isothermal process. So in an isothermal process, dq is equal to dw. Next, coming to the adiabatic process. We know that in an adiabatic process, the quantity of heat Q remains constant. Quantity of heat Q remains constant. That means dq is equal to 0. So the first law of thermodynamics for an adiabatic process reduces to du, this is dq is equal to 0, hence du is equal to minus dw, or we can also write it as dw is equal to minus du. That means in an adiabatic expansion process, positive work is done, hence work is done by the gas, hence there will be decrease in internal energy. Whereas if the work in the case of compression process, dW is negative, work is done on the gas, hence there will be increase in internal energy. So this is regarding the adiabatic process. Next, coming to the isochoric process. In an isochoric process, volume remains constant. When volume remains constant, dV is equal to 0. We know that work done dW is equal to P into dV. So P into 0, that becomes 0. So dW will be 0 in the case of isochoric process. Then the first law of thermodynamics for an isochoric process reduces to dq is equal to du. This implies that if the heat is supplied to a system, then internal energy of the system increases. Conversely, if the heat is given out of the system, the internal energy of the system decreases. Next comes the cyclic process. What is a cyclic process? If a process reaches its initial state after undergoing a number of changes, then we call it as a cyclic process. In the case of a cyclic process, the internal energy U is constant. This implies du is equal to 0. Then the first law of thermodynamics for cyclic process reduces to dq is equal to dw. This implies the net work done in a cyclic process is equal to the net amount of heat transferred. Net amount of work done is equal to the net amount of heat transferred. So we have seen how we can apply the first law of thermodynamics to various thermodynamic processes: isothermal process, adiabatic process, isochoric process, and a cyclic process. Now let's see the limitations of first law of thermodynamics. The first law of thermodynamics is having some limitations. The first one is it does not help to predict whether the certain process is possible or not. The reason for this is it does not specify that heat cannot flow from low temperature body to a high temperature body. Of course, we know that heat always flows from a body of high temperature to a body of low temperature. But this first law of thermodynamics does not specify that heat cannot flow from low temperature body to a high temperature body. The second limitation is it does not give information about the direction of heat transfer, about the direction in which the heat transfer is taking place. The reason for this is it puts no restriction on the direction of flow of heat, whether heat can flow from a cold body to a hot body or vice versa. The third limitation is it does not provide and specify sufficient condition for the process to take place. That means this law is silent about its percentage of conversion of energy from one form to another form. According to this, work can be converted into equivalent amount of heat, but heat cannot be converted into equivalent amount of work. So these three are some of the limitations of first law of thermodynamics. To overcome these limitations, another law is needed, which is known as the second law of thermodynamics. Hope you have followed this first law of thermodynamics, its applications and limitations useful. Thank you.